At this point, you might be wondering, how are uniform random variables drawn? So now we're going to introduce uniform pseudo-random number generators. Suppose we want to draw u1 all the way up to un, such that for each I between 1 and n, and each a between 0 and 1, we want the probability that ui is less than or equal to a to be approximately equal to a. The former ensures that the CDF for the u's that we draw is quite close to the theoretical CDF for the uniform 0-1 distribution. In addition, we want u1 all the way up to un to be looking like they are statistically independent. And we want the u's that we draw to have a very long period so that the samples do not cycle back. In other words, at some point with a large n, u1, u2, etc. starts to repeat themselves again. We don't want this to happen for a long while. In other words, for large n's, we don't want u's to cycle back. So how can we draw these numbers so that they can satisfy these properties? Before introducing that, let's discuss something called pseudo-random number generators, or PRNGs. So in R and in a lot of statistical softwares, pseudo-random number generators are used to generate these random numbers or to generate variables from the uniform 0-1 distribution. PRNGs are available for generating a sequence of actually deterministic, so not random, numbers whose properties approximate those of random numbers. So although they are actually not random, they look like they're random. There are many algorithms that are available for PRNGs. So there are different algorithms that can be really complex for generating these pseudo numbers that look like they're random. If you are interested in this, you can do !randomseed inside R and see what are the possible options of PRNGs in R and what each of them is called and what kinds of algorithm they implement. In addition, there are statistical tests for the quality of these PRNGs. As a fun fact, you may want to read the Wikipedia page on the die-hard tests. So here's the Wikipedia page for this, and it says that the die-hard tests are a battery of statistical tests for measuring the quality of random number generators. So it's a series of tests, and I really don't know how they came up with this series of tests, but some of the tests inside this test battery, such as the monkey test, look really funny. Okay. So we're going to introduce a basic PRNG, which is used as the basis of many more advanced PRNGs. You can look up the more sophisticated ones. For example, the one that is used by R by default, which is called the Mersenne twister, yourself. The one we'll introduce is called linear congruent number generator. So instead of considering drawing something between 0 and 1, let us first consider drawing integer samples between 1 and p, where p is a very large prime, such as the Mersenne primes, which is 2 to the power of something minus 1. For example, the Mersenne prime, this is one of the Mersenne primes. So 2 to the 31st power minus 1, which is this really large prime number, may be used as p. In step 1, we want to choose the initial value. So we want to have a u star. So that's the integer sample we want to draw. U star 0. So sample 0 we want to draw, which is a initial integer between 0 and the large prime p. And this is known as setting the seed. So u star 0 is the seed. Its initial value actually determines what the subsequent values are. In step 2, we want to obtain subsequent draws. So for each I equals 0, 1, 2, etc., we want to set u star of I plus 1, which is the I plus 1 pseudo-random integer sample, to be equal to A times ui star, the previous pseudo-random integer sample, plus C modulo P. So here, A is a constant multiplier in front of the previous draw. C is called a constant shift. So when C is set to be equal to 0, then ui plus 1 star is simply equal to A times ui star modulo P. In that case, this is called a linear multiplicative concurrential number generator. And then mod over here denotes modulo. So in general, n mod p gives the remainder of n divided by p. In other words, u star at the I plus 1th draw is the remainder of A times ui star, the previous draw, plus C divided by the large prime P. So you can see that the draws we will obtain will always range between 0 and P because we're taking the remainder divided by the large prime P. So the next step is to convert this to something that's between 0 and 1. So right now we have random integer samples between 0 and some really large prime. So these are really large integer numbers. How can we transform them into something between 0 and 1? Well, this is actually quite easy. So we can rescale them by dividing them by p. So let's set ui to be equal to ui star, which is the ith integer draw divided by the large prime p. And the resulting ui's will range between 0 and 1. We won't go into the details of the theories behind these algorithms, but you can read the information online yourself. So using these kinds of methods ensures that each of the integers between 0 and p have approximately equal chance of being sampled. And in other words, after rescaling, the resulting ui will theoretically follow the uniform distribution between 0 and 1. So let's briefly discuss something called setting seed in R. So maybe you already know this, then you can skip this part. So previously we discussed the initial draw. So u star 0 is known as the seed. That's when the sequence starts. Once that's fixed, everything afterwards is fixed. In R, you can set the random seed using the setSeed function. So if you're interested, you can go to your RStudio and do the following exercise. Step 1, try to draw 5 samples from the uniform distribution between 0 and 1. And then draw another 5 samples from U0, 1. You can take a look at the 2 sets of samples. So 5 uniforms first time and 5 uniforms second time. And check if you got the same values. Hopefully no, because every time you generate these pseudo-random numbers, you want the results to be different so that they look random. Now do the following. Set your seed to some number. So for example, you can set your seed to 1, 2, 3, 4, 5 by doing set.seed 1, 2, 3, 4, 5. And then you want to do step 1 again. Again, you draw 5 samples from U0, 1. And then you set your seed back to 1, 2, 3, 4, 5 and redraw uniform 5 uniform samples. So if you set your seed to this number, draw 5 samples, and then set your seed back to this number and draw the samples again. This time, you can check whether you get the same values. Hopefully, you will get the same values because you have set the random seed to some fixed initial number. So this illustrates something. So setting seed allows us to control the random samples that are drawn every time. If you fix the seed, then you're going to fix the random samples you will obtain from R every time. This can be really useful for doing simulation studies and doing a lot of scientific studies because it allows us to get replicable results. That is, for someone else, if they want to run your code and get the same result as you did, then they just need to set the seed at the beginning into the seed that you set at the beginning as well.